All right, today we're tackling one of the most powerful and, let's be honest, seriously disruptive technologies on the horizon: quantum computing. Now, this is a technology that promises to change, well, pretty much everything, from medicine to making new materials, but it also carries a massive threat to our entire digital world.
And don't just take my word for it. Let's start with this pretty stark warning from the NSA. For them, this isn't just some cool science project, it's a huge global security issue. What they're saying here, in no uncertain terms, is that the very foundation of all our digital security, the locks on our bank accounts, on government secrets, everything, could be made completely worthless.
And look, this isn't some far-off future problem. This threat is happening right now. Adversaries are actively sucking up huge amounts of our encrypted data, just hoarding our secrets, and they're betting that in the next decade or so, they'll have the quantum key to unlock every last bit of it. Think about it. Information that's secret today is still going to be valuable tomorrow.
So before we can even get to the solution, we first have to really wrap our heads around the problem. We need to understand the digital locks that we all use every single day, and why this ticking clock of quantum computing has basically put all of our current secrets on a deadline.
For the last 40-plus years, this one principle, it's known as RSA encryption, has been the absolute bedrock of our secure world. That little padlock you see in your browser? Yep, that's the math protecting you. For a normal computer, even a massive supercomputer, trying to break this lock by working backward from the answer would literally take millions of years. It's a lock that has been, up until now, effectively unbreakable.
So, how is this new kind of computing even possible? Well, it all comes down to its fundamental building block, which is completely different from the computers we're all used to. And this is where things get a little weird, but also unbelievably powerful.
Okay, here is the absolute key difference. The computer or phone you're using right now runs on classical bits. They're just simple on or off switches, a 0 or a 1. That's it. But a quantum bit, or a qubit, is a whole different beast. It can exist in a weird blend of both states at the exact same time. It's less like a light switch that's on or off, and more like a dimmer dial that can be anywhere in between.
This bizarre state is called superposition. And what's crucial to get here is that this isn't because we're just not sure which state it's in. No, it's a fundamental property of how the universe works at this tiny scale. The qubit is genuinely, truly in both states at once, which lets a single qubit hold way more information than a classical bit ever could.
And that brings us to the next piece of this quantum puzzle, entanglement. This is where things get really wild. When you link qubits together, their power just explodes exponentially. So 2 classical bits can be in one of 4 states, right? But 2 entangled qubits exist in a superposition of all 4 of those states at the very same time. They're not separate things anymore. They act as one single, much more powerful system.
Okay, so you take these 2 crazy principles, superposition and entanglement, and you put them together. Let's explore the truly mind-bending computational power they unlock.
This right here is the secret sauce of quantum power. It's not just a small improvement. We're talking about exponential growth. 2 qubits can process 4 states at once, okay? 3 qubits can process 8. 20 qubits can process over 1 million states at the same time. This is a leap in power that classical computers just can't, and never will, match. Now, let's put this into perspective. The number 300 itself isn't the magic part. It's what it represents. With just 300 perfectly entangled qubits, a quantum computer could explore more possibilities at the same time than there are atoms in the entire known universe. I mean, just try to wrap your head around that. It's an almost unimaginable amount of parallel processing power.
I love this way of thinking about it. A classical computer is like a bloodhound, checking every hiding spot on a list one by one by one. But a quantum computer, because of entanglement, can kind of nudge every single possibility at the exact same time, zeroing in on the right answer with incredible efficiency.
So, let's bring all this immense power back to the problem we started with, encryption. Let's see exactly how this powerful new tool can pick those unbreakable locks we talked about.
The secret weapon is something called Shor's algorithm. And here's the trick. While a classical computer just gets hopelessly stuck checking endless possibilities one by one, a quantum computer is uniquely brilliant at one specific task: finding a repeating pattern, a period, buried inside that massive haystack of possibilities. It uses its quantum nature to spot a hidden cycle in the math, and that cycle is the key that basically blows the whole lock apart. And this chart really shows the staggering implication. A problem that would take our absolute best supercomputer today, something like 16 million years to solve, could theoretically be solved by a big enough quantum computer in a few minutes. That's not just picking a lock, that's vaporizing the entire door.
So, with the old locks effectively broken, a global race has kicked off. Cryptographers, mathematicians, governments around the world are all working like mad to invent and deploy a whole new generation of security. New locks that can stand up to attacks from both classical and quantum computers.
And you can see this isn't science fiction. It is happening right now. The U.S. National Institute of Standards and Technology, NIST, has been running a worldwide competition to find and standardize these new quantum-proof algorithms. And after years of battle-testing ideas from all over the planet, they've already picked the first set of winners.
So how does this new defense even work? Well, a lot of the new methods are based on a totally different type of math problem. Instead of factoring numbers, it's more like trying to find a specific point in a super complex high-dimensional grid called a lattice. And it turns out this is a problem that, as far as we know today, is just incredibly hard for any kind of computer to solve if you don't have the secret key.
This is the perfect analogy for it. Think of it like this. Your secret key is the map to a ridiculously complex, thousand-dimensional maze. With that map, finding your way is easy, for you. But for an attacker, even a quantum attacker who doesn't have your map, finding their way through that maze is practically impossible.
And so, this leaves us with the critical question, the ultimate question, really. The race is officially on. But it's not just about inventing these new, stronger locks. It's about the absolutely massive job of replacing every single digital lock across the entire internet, in our servers, our phones, our cars, before that ultimate quantum key is finally built.